So I'd like to echo Mike Hoschella's thanks to George Calas for organizing this wonderful colloquium in Paris, which is my favorite city in the world, and so it's really a pleasure to be here. So I'm going to take a different perspective than has been taken so far. I'm going to look back in history a little bit at some of the mining practices and some of the consequences of those practices in California, which is what I'm familiar with, and I'll actually speak a little bit about a trip I recently took to Paracatu, Brazil, to see a gold mine as well. So I'll cover the sort of the environmental legacy of these three materials, gold, mercury, and asbestos, and show you how they're linked together, and look at some of the long-term impacts and how we can possibly mitigate them. So just in case you don't understand anything I say today, I decided I'd just tell you right up front what I want you to get out of this talk. So here are my points, and then I'll hopefully cover these. So the gold rush that began in 1848 and the initiation of mercury mining in California are really very intimately related. By the way, mercury mining began about 1850. And that's because once the coarse-grained gold was found by prospectors and 49ers and so forth, they had to use liquid mercury to recover the fine-grained gold. So that was why that was so connected. And there's also a legacy from the gold mining in California at other locations, such as in Paracatu, Brazil. And that is that gold is often present as intimate inclusions in fact, at the molecular level, in things like pyrite, sorry, not gold, but arsenic is present in pyrites, and also arsenopyrite, which are common sulfides associated with gold ore. And so as a result of that, it's very common for there to be major contamination in the areas of gold mines with respect to arsenic, way above the World Health Organization MCL for arsenic of 10 parts per billion. The legacy of mercury mining in California and the use of liquid mercury to recover fine-grained gold is also significant because there's continuing input of mercury into the San Francisco Bay ecosystem via rivers that drain the gold country in the Sierra Nevada foothills, and also the rivers draining the California Coast Range, where over 2,000 mercury mines were once in operation. I'll try to get across to you also that knowledge of the molecular level speciation of mercury, and for that matter arsenic as well, is very necessary for determining if remediation of these polluted soils, sediments, and mine waste is needed. And I'll introduce to some of you, and some already know this very well, that synchrotron-based spectroscopy using very, very intense X-rays can provide those details about the speciation of things like mercury and arsenic. One of the things we found is that a major form of transported mercury is nanoparticulate mercuric sulfide, which follows up on what Mike was talking about. Furthermore, we developed a new X-ray absorption spectroscopy method that we use to show that mercury evasion, that is mercury evaporation from mine waste, which produces much of the mercury pollution in the atmosphere around the entire globe, is controlled by the presence of liquid mercury. And finally, I'll just hit very briefly on an associated material, asbestos, which occurs near the mercury mines in California, Central California. And these are major point sources for airborne fibers that we're breathing right now as we sit in this room. Okay, so that's basically what you're going to get out of this talk, in case you're going to go to sleep now, actually, and I'll wake you up at the end. So just history of gold mining. Well, as you all know, the first discovery of gold in a place called Sutter's Mill near Coloma, California, happened in January 1848 by a guy named James Marshall. And the word got around very quickly, and this resulted in a fundamental change in California as we know it. Brought about 300,000 people from the rest of the U.S. as well as all over the globe to take advantage of this new discovery. For example, San Francisco grew from around a population, can you believe this, 200 people in 1846 to a boomtown of 36,000 residents in 1852. It really wasn't the miners who got wealthy, it was people that supplied the miners. For example, I know members of the Haas family, which own the San Francisco Giant baseball team and other things like that, and they were the producers of Levi's jeans. And they sold mining supplies to the miners in the form of picks and shovels and jeans, and they made a fortune. And so they were the ones that really benefited from this. Now, we talk about environmental impacts. I think one of the most incredible impacts I can imagine is that these gold miners that came in literally wiped out the Native American population. They slaughtered them on the lands that they were trying to take over for gold. So that was, for me, that's an even bigger environmental consequence than simply pollution. Here's a picture of a 49er panning for gold, and if you've never done this, this is a lot of work. I've done this before just for fun, but you get tired real fast. And then here's one of the ways that mining proceeded. This is called hydraulic mining, using high-pressure water hoses to basically wash away sediments downstream to release the gold from these sediments. And this is where amalgamation of the gold with mercury was used. But in 1851, after a lot of the simple stuff had been depleted, hard rock mining became a major method for gold production, and it was basically in the form of quartz veins. So a lot of gold was produced from the beginning of the gold rush until today, and then this is a statistics that's interesting. For over the 7,000 years that gold's been mined on Earth, about 5 billion troy ounces has been produced, and California and Nevada contribute about 5% of that total. So let's look at mercury just for a minute. It's the only common metal that's liquid at room temperature. It's known as quicksilver. It alloys very easily with things like gold and silver and is used to amalgamate fine-grained gold during the California gold rush and beyond, even today. Mercury pollution occurs through these mining activities that we'll talk about: fossil fuel combustion, industrial release, for example, chlor-alkali plants, and also naturally from volcanic activity and hot springs. The mercury bioaccumulates in the food chain, particularly in predator fish such as tuna, which is a major vector for mercury in the form of methyl mercury in humans. These methyl mercury compounds have neurotoxic effects, all sorts of problems, including death. And I've got pictures up here of the so-called Mad Hatter from Alice in Wonderland, who was forming beaver skin hats with mercury vapor, which was a very common practice back in that day. And then more recently, of course, the terrible Minamata disease in Japan, which caused huge amounts of damage and killed about 12,000 people. Anyway, the current U.S. EPA maximum contaminant level for mercury in drinking water is about 1 part per billion, so it's one of the most sensitive of all pollutants that we deal with in terms of the small amount needed to cause damage. So here's a location of mercury and gold mines. The golds are, of course, in gold colors. The mercury mines are in red. That's the California Coast Range you see going down the coast of California. Here's the gold country in here that we typically think about, the Klamath Trinity Mountains up there as well. And, of course, lots of gold mines in Southern California as well. So here's some of the sluices where the mercury is put into the bottom of each riffle. And at the end of the day, that material was taken out, retorted. And as you'll see, a lot of that mercury was volatilized and lost to the environment during the retorting operation. This is how these deposits in the California Coast Range formed. There was subduction that occurred over much of the history of California up until about 25 million years ago, and then things changed substantially. We went from a subduction type of tectonic region to a strike-slip fault, the San Andreas Fault. And that those subducted slabs began breaking up, as you see here in this cartoon, and the result was that the heat flow became much more significant through those so-called slab windows, and it basically created hydrothermal fluids which mobilized things like mercury, gold, silver, and so forth, and brought them up to the surface where they were deposited in the form of various mines. This is a slide just about the chemical properties of mercury. I just want you to focus on one thing here. The melting point of mercury is minus 38.9 degrees C. I'll give you a quiz about this in about 10 minutes, so please remember that number. It's going to become important. Also, just one quick thing. There's some stable isotopes here. I'm not going to talk about stable isotopes, but we've been doing some isotope geochemistry on mercury. We can now basically trace where mercury comes from by using stable isotope ratios of these mercury isotopes. That's very interesting, especially in fish. So just to show you, there are lots of mercury-containing phases. Here's a list of them, and this is not even all of them, but in blue are the ones that we typically encounter in some of these mining sites for mercury. And in particular, the biggest ore of mercury is cinnabar, this right here, which is just simply mercuric sulfide in hexagonal form. Here's a picture of what some of the ore looked like at New Almaden in California. You can see why it's called strawberry ore. Looks like strawberries. Here's global production, and it also shown as the production from the Almaden mine in Spain and the Idria mine in what was formerly Yugoslavia. But you see that it really peaked up during the Second World War, and then it came crashing down as we discovered some of the potential impacts of mercury on human health. As a result of those impacts of various types of uses of mercury, we are now looking for alternative products that can take their place. In some cases, we simply can't find them, but there's simply a huge number of ways that mercury is used in various consumer products. Here's how the global anthropogenic emissions of total mercury to the atmosphere have changed over time, and you can see in Asia they're going up, in places like Europe, and also in North America they're going down. And so a lot of them, in fact most, if not all of the mines for mercury have been closed in these parts of the world. So lots of bad publicity for mercury, especially in California where we have all these mercury mines. Here's the dump at the New Albany site now. It's no longer there. It's been covered up and remediated. It was a Superfund site. Here's Clear Lake, the sulfur bank mines, and a lot of the material from the waste went right into Clear Lake, which is not a good idea. But what I'm going to try to prove to you is that determining the speciation of mercury, that is at the molecular level, in these contaminated wastes can help us really predict the long-term mobility and whether or not we need to remediate sites at great cost, I might add. So, in terms of mercury production in the California Coast Range, we produced about 220 million pounds of mercury between 1850 and 1981, and about 26 million pounds of this was used for gold recovery in the Sierra Nevada and Klamath Trinity Mountains. The bottom line is we lost about between 3 million and 8 million pounds of mercury in these operations to the environment in the Gold Country. Now, the Gold Country sits right up in this area here. You can, if you look carefully, you can see all these streams. So all these things coalesce to form a stream, the Sacramento River, that goes right into San Francisco Bay. In addition, we have all of the mercury mines in the California Coast Range, and streams and reservoirs there, of course, receive mercury, which is transported in a way that we'll talk about in a few minutes. But the point is that there's a lot of drainage that goes right into the bay from the South Bay and the North Bay that contains mercury. So here's a picture of where I live, and Stanford's about right in this area here. Anyway, one question that's often asked is there more mercury coming into the South Bay or into the North Bay from all the Sierra Nevada drainage, South Bay from the drainage from the Coast Range where the mercury mines are located? A friend of mine, Professor Slagle at UC Santa Cruz, has spent his life measuring the amount of mercury in these different localities. It turns out that there's 7 times more mercury coming into the South Bay from what's called the Guadalupe River than from all the massive input from the North Bay. So it's a really interesting difference. We also have just found out, not too long ago, that there's also mercury coming into the Bay Area from refineries in places like Richmond. They're refining oil and basically oil from the Central Valley, which is very sulfur rich. And one thing about mercury that you probably have already figured out, it likes to bond to sulfur. So there's lots of mercuric sulfide in these oils, and this is a real major problem for groups like Chevron and ExxonMobil when they're refining the oil. So the mercury is associated with serpentinite deposits. There's a huge serpentinite massif. That's a place I take my students every year. There's some silica carbonate alteration, nature's way of basically sequestering CO2. You can form magnesite very nicely. You can also take things like ultramafic rocks, react with silica and a little bit of water and produce serpentine, the California state rock. So this is the belt where the mercury mines are located right in here. This is what a simple geologic map looks like of the area. This pink stuff is the serpentinite. The mercury mine, the second largest mine in North America, is located right there, and there are faults bounding both sides of this massif. This is what the mine operation looked like in 1910, and this is what it looks like in 2010. I took this picture 100 years later, and this mine operated between 1858 and about 1972, and it was the second largest producer of mercury in the U.S. Here's an acid mine drainage pond from these waste piles. And I showed this for 2 reasons to show you. First, that it's quite acidic. And secondly, I want you to focus on this sort of cloudy film that sits on top of the water at this site. And also the white effluent here, which is basically Epsom salts, magnesium sulfate hydrate. But it's that cloudy film that's interesting because that cloudy film is a microbial biofilm. And one of my students, Adam Jew, just finished his thesis with me. He's now a postdoc with me. And what he discovered was that the presence of these bacteria can take a otherwise extremely insoluble mineral, mercuric sulfide, has a solubility product of 10 to the minus 52, which means if you put it in water, it just sits there, doesn't do anything, doesn't release anything over millions of years. But in the presence of these bacteria, including Thiomonas species, the solubility product of cinnabar is reduced. By that I mean it's made less negative by about 30 orders of magnitude. So a mineral that has been declared by the EPA as not a problem, it's benign environmentally, all of a sudden becomes a problem, particularly when it's in the form of nanoparticles. As Mike pointed out, nanoparticle properties can be vastly different from their bulk counterparts, and one of those properties that's really important is solubility. So the solubility of a nanoparticle is going to be much, much greater than the solubility of a piece of bulk cinnabar. And you add to that the effect of these bacteria, you've got a real problem. So this is where a lot of the mercury is coming from these acid mine drainage ponds with microbial interaction with these minerals. Releasing mercury in the form of mercury 2+, which can then be methylated by sulfate and iron-reducing bacteria. And that's the form that is transmitted into fish and ultimately into us. The calcine, this is after roasting the ore, is dumped in the stream valleys. This is at New Italy also. These sort of piles of reddish-pink material are the calcine materials. We've done a lot of work on that. This is basically the old furnace house. The big rotary furnaces are in here at angles, and this is where the material came out into dump trucks like this, which then carried them over to the side here and dumped them down into the stream valley. This is a schematic of what the roasting process looked like. Here's one of these Archimedes screw wheels that the furnace, which operated at about 700 degrees C. The vapors went up into a condenser, set up condenser coils, where the mercury vapor solidified into liquid mercury, came out into spigots here, into rubber buckets, which were then were used to fill these metal flasks, which hold about 76 pounds of mercury. The problem, of course, is that you have also gases that escape into the atmosphere. And so this is what the condenser coils in New Italy looked like a few years back. Now they've been destroyed by hunters and other people that like to destroy things like this. So they're just a shambles now, but this is what they did look like. So these are stainless steel condenser coils. Now, okay, so focusing on one thing here, a guy named Schutte, he was a mining engineer back in the 30s, who went around to various mercury mines and studied the output of these stacks in the form of mercury vapor. And he concluded that about 85 pounds of mercury per day per furnace was generated in the form of mercury vapor that came out of the stacks and was lost to the environment. And that totals up to 340 pounds a day from the New Italy mine alone. This, if you think about the fact that these mines operated 24 hours a day, 7 days a week for almost 100 years, that's a lot of mercury into the environment. About half of which goes basically into the soils locally, and about half of which goes into the atmospheres and then trained in a global type of stream of mercury. The stuff that locally deposits, of course, enriches the soils in mercury, and you can see how much we have here. We have 5,000 parts per billion, 5 parts per million, which is a lot of mercury. It, of course, falls off pretty rapidly as you go down into the soil. So, again, we need knowledge of the molecular level speciation of mercury if we are to determine if a site needs to be remediated. The method of choice for this, as I've already sort of alluded to, is the synchrotron-based method known as X-ray absorption spectroscopy. I know that some of you don't know what a synchrotron is, so the question is, what's a synchrotron? Glad you asked. This is the first synchrotron, which was built in Schenectady, New York by the General Electric Company. It was a 70 MeV synchrotron, and basically a synchrotron is a device that produces very intense light because you're taking an electron beam and you're bending it with bending magnets. Every time that the electron beam undergoes a bend, it loses energy in the form of synchrotron light. That energy comes off in basically rays tangential to the circumference of the ring. Here's the largest ring in the US. It's called the Advanced Photon Source at Argonne National Lab outside of Chicago, with many, many beam lines, and you notice that they're all sort of tangential to the ring as you go around. The light's coming off tangential to that ring. We have beam stations where we do experiments. We can use these extremely intense X-rays to study things such as mercury speciation. I couldn't help but show a picture of the major new light source here in France, not too far south of Paris, called Soleil, and I've been there several times serving on committees. This is the ring itself, and again, we have electrons being guided around this ring by magnets. We input energy in the form of radio frequency, and otherwise you'd have a loss of energy entirely after a while, but the electrons are re-energized by these radio frequency cavities as they circle around this big ring and produce this beautiful, intense synchrotron light. So this has really revolutionized science, and that's the reason for that is because of this plot right here. So X-rays were invented by Röntgen back in 1895. You might remember the picture of his wife's hand that he took, showing her bones, and so this stuff called X-rays penetrates matter. I did my PhD thesis right in here at Virginia Tech. I could now do my PhD thesis. That took me about 1.5 years to collect the data. I could now do my entire PhD thesis in one morning at the Stanford Synchrotron Radiation Light Source. That's how things have changed over my lifetime. And so what's happened, of course, with synchrotrons is we've pumped basically the so-called brightness up enormously. This is about 10 to the 7th here. And when I first started doing this, I was right in here, but now we're up to here. That's 10 to the 20th. And then we have now this new light source called, it's an X-ray free electron laser at SLAC, called the LINAC coherent light source. And we're now up to about 10 to the 34th in terms of brightness. Anytime you change things by a few orders of magnitude, it often leads to a revolution in science, but think about changing things 20 or 30 orders of magnitude. That's really a revolution. So we can do things we simply could never even dream of before using these sources. One quick thing, the greater the brightness, the smaller the sample can be, and the smaller the element concentration can be, and that's really important because, as you'll see, some of these concentrations of contaminants are very low. But we can study them using these X-ray methods. So the technique we use is called X-ray absorption spectroscopy. We basically knock inner core electrons out of the inner orbits of things like mercury atoms. They go out as photoelectron waves. They're scattered and backscattered by the surrounding ligands, in this case maybe oxygens or sulfurs. And it's this interference between the outgoing photoelectron wave and the backscatter wave that produces these oscillations that are called XS spectra, which stands for Extended X-ray Absorption Fine Structure. So that's the type of spectroscopy we do, and this is a schematic of how that basically operates. The X-ray beam goes through the sample, and then it fluoresces into this detector here, and we can monitor that and obtain spectra that look like this, which can be analyzed to produce information about the surroundings of the mercury atom, the valence state of the mercury atom, and so forth. In sampling, we did a lot of sampling of different types of deposits, and here's my former student, Chris Kim, who's sampling one of these calcine piles. And these are the type of spectra we get from different mercury-containing minerals. I want you to focus on this thing called elemental mercury, mercury 0. The liquid mercury, you see the spectrum is basically useless because there are no features in it. But we're going to fix that in a minute using that number that I asked you to remember. So here are some of the concentrations of mercury. Some are really large, but others are small, like, for example, 250 parts per million. And again, we see that there are some differences in these spectra from the different mine sites, and we're going to analyze those and understand speciation from that. This is just a way that we fit the data. For example, we have an unknown spectrum here from the Turkey Run mine, and here's the spectrum of cinnabar and the spectrum of metacinnabar, both mercuric sulfide, one hexagonal, one cubic. And you notice that these spectra are out of phase, which means we are able to fit these two different components. And so this is about 60% cinnabar and about 40% metacinnabar in this sample, using a technique known as linear combination, least squares fitting. This is just some of the results from different mines. These are waste rocks and calcines we looked at, and the ones that are in red here are the ones that are the problem. I mentioned that cinnabar and metacinnabar are relatively insoluble unless bacteria are present, but these other minerals, such as corderite, are extremely soluble, and this is where the mercury is released from these very, very soluble minerals. So if you have phases like this present in your deposits, then you have troubles, and these probably need to be remediated. And a lot of them have been declared Superfund sites in the U.S. and worked on. Just to go through this quickly here. Here's another whole list of things. Again, you see some of these red things, these minerals that are extremely soluble. And when you find those, you basically need to remediate that material. So one other thing I'm not going to go into, but the speciation, of course, is very dependent on geologic origin of the deposit. So we have both hot springs deposits as well as silica carbonate deposits that mercury is found in. So the next question I'm going to address is, where does the mercury in the atmosphere come from? Because there's lots of it. So we did a lot of work. We actually deployed mercury collectors out into various mine sites, looking at the mercury that evades or is sort of evaporating from the mercury containing waste material. We were able to collect spectra on that material. And one thing that we did, and again, back to that number, the very low melting point of mercury, minus 38.9 degrees centigrade, we were able to freeze the samples very slowly so that the mercury that's liquid crystallized into alpha mercury. If we'd basically lowered temperature rapidly, we'd have turned it into a mercury glass. But in this case, we cooled it very slowly. We created this new technique, a cryo technique, which allowed us for the first time to see, using X-ray spectroscopy, the presence of liquid mercury. And that, of course, here are the spectra. Again, you see they're all out of phase with respect to each other. Liquid mercury, centibar, and metacentibar. So again, we can easily go back and fit these data. And now for the first time, we find lots and lots of liquid mercury present in these mine wastes. And we were able then to correlate, I'll just skip right to it, the amount of mercury in the form of liquid mercury with the mercury flux coming from these deposits as in the form of vapor. If you just simply plot total mercury, you get this crazy plot that means nothing. But if you look at liquid mercury only, you've got this nice correlation. So this is the reason for the evasion of mercury from different mine sites. And different mine sites have different amounts of liquid mercury, therefore they have different evasion values as well. We also found, after lots of electron microscopy, Mike's a real specialist in electron microscopy, so he knows how hard this is, but we spent literally a whole year looking for the needles in the haystack, and we ultimately succeeded finding small particles, nanoparticles of mercuric sulfide present in sediments. And this is the form that mercury usually travels in. Even the stuff that was taken up to the Sierra Nevada foothills for the amalgamation with gold, there was no mercury up there at all before we took the liquid mercury for that process. But that liquid mercury is now being converted into nanoparticles of mercuric sulfide. So one of my students, Aaron Slowey, did a thesis in which he found that the major components of mercury that are being transported from the Sierra Nevada foothills down to the bay are in the form of mercuric sulfide nanoparticles. Okay. But mercury also comes from the burning of fossil fuels. So here's a power plant, a coal-fired power plant in Laughlin, Nevada, producing a lot of mercury. There are about 600 of these plants in the U.S. now, producing about 40% of our electricity. And these are also the main sources of mercury pollution in the atmosphere. So let's now go to the byproduct of gold mining, arsenic, and you can see the distribution of arsenic in California in the Sierra Nevada foothills from the gold mining area and here in the Coast Range as well. And so the reddest points here are greater than 50 parts per billion, which is 5 times more than the MCL for arsenic. We have some hot spots that have really caused lots of attention. People have built houses on tailings which have huge amounts of arsenic. In fact, I was up visiting the Mesadoro site a few years back, and there were kids in the yard that was otherwise bare. No grass grows in this stuff. Playing with little Tonka trucks, filling them up with the dirt, breathing the fumes, not good. In these particular types of deposits, these mother lode are lode deposits of gold. These are basically quartz matrix deposits, but they contain significant amounts of pyrite, which is, by the way, called arsenious pyrite because they contain arsenic. There's also, of course, arsenopyrite, which is this ore right here, iron arsenic sulfide. So these are less abundant than the pyrites, but both contain abundant arsenic, and this is where the arsenic typically comes from, associated with gold mines. This is Andrea Foster's thesis, one of my former students, who's now a geomicrobiologist at the USGS in Menlo Park. And looking at these, again, sediments at gold deposits, we were able to speciate the mercury using XS spectroscopy. And we found that a lot of it is actually associated with iron oxides in the form of adsorbed arsenic. That is, arsenic is present on the surfaces of these minerals. Then I had the privilege of visiting a very great site in Paracatu, Brazil, about 2 months ago. And my host was Virginia Simonelli, a professor of metallurgy at the University of Minas Gerais in Belo Horizonte. And this is a picture of that mine. It's a huge open pit mine. The main ore, you won't believe it, is phyllite. You might ask, why in the world would phyllite be useful as an ore for gold? Well, turns out that the grade of the ore is really quite low. It's 0.4 grams per ton. Most people wouldn't touch that, but there's such a massive amount of this stuff here that this is a very, very economically viable setting. So here are the various minerals again that are present: arsenopyrite, arsenian pyrite, scorodite's one of the weathering products of this. We also have, of course, realgar and cinnabar, realgar and orpiment shown down here. All, of course, sources of arsenic. Here's a plot that's probably proprietary. I probably shouldn't be showing this, but I am, of the distribution of arsenic in the soils around Paracatu. And you can see again, this is 150 parts per million in the soils in these red spots. So a very, very contaminated site in an otherwise extremely environmentally conscious operation. In fact, here's some of the holding ponds. They put in about 60 million tons of the waste material a year, containing lots of sulfides. These ponds only have about a foot of water covering the waste material, and this basically has eliminated the problem of acid mine drainage. No problem at all. Unfortunately, the arsenic is still there as a major problem, though. Some of the metallurgical work that they've done down there, they do a lot of bioleaching. In fact, the whole operation involves bringing massive quantities of the raw material, putting them into large jaw crushers, then putting them into gigantic ball mills that are almost the size of this auditorium. There are 4 of them operating all the time. From that, it goes into basically a liquid separation process for separating the sulfides, and then it goes into a cyanide leach to extract the gold. Very complex operation, very well done, though. Finish up quickly, the same problem about arsenic present in some of the ores in which we have gold is also a major problem in South and Southeast Asia, and this has resulted in the largest poisoning, mass poisoning in human history. Over 100 million people are affected. And the main reason for showing this, it doesn't really fit into my talk except for the following reason, is that most of the arsenic pollution on Earth is from natural sources. In this case, from the pyrites that are arsenic rich and the arsenopyrites that are present in the Himalayas that are weathered. The arsenic is released in the form usually of arsenic 5. It's transported from the Himalayas and the foothills of the Himalayas down major rivers into the deltas where it's deposited, and it's transported mainly as arsenic sorbed on iron oxide and hydroxide nanoparticles. Back to Mike again. The importance of those I can't overemphasize. When they're deposited, bacteria, of course, are present, and they're stimulated by human activities as well. But these bacteria are basically iron-reducing bacteria, things like, well, just various ones. There are many of those varieties, and these things reduce the iron. This shows a schematic of a bacterial cell wall. Electron transfer is taking place to these arsenic-sorbed iron hydroxides, and this reduces the iron from 3+ to 2+. The iron hydroxide basically literally falls apart, and the process releases the arsenic 5+, which then is reduced by the same bacteria to arsenic 3+, the most dangerous form of arsenic for humans. And this is what they drink in the tube wells that they have put in there. So I've got one simple chemical reaction that sort of describes this whole process that I sort of simplified here. So I just want to finish up by talking about something closely associated with the mercury deposits. These are asbestos deposits. I've done a lot of work over the years on this. I've done lots of expert witness testimony. This is a very interesting figure we generated for one of our trials, showing what these fibers look like, rolled up sheets basically. This is what it does when it gets into the human air system. We have what is called a mucociliary escalator that tries to keep particles moving up our throats and out of our lungs. It works pretty effectively, but even more effective are these things called macrophages, which try to engulf the particles. This is an actual macrophage engulfing a particle of asbestos shown here. So another byproduct of mining, in this case of asbestos, is human disease. In fact, lung diseases of various sorts. cancers, and lots of controversy about this. Now it's pretty well determined in the court system, and at least in the U.S., that chrysotile asbestos, the stuff that's associated with serpentine, is not a major cause of disease. Instead, it's the amphibole asbestos minerals that are. And so a lot of my testimony has to do with, are there any amphibole asbestos minerals in the chrysotile asbestos? And if there are, then that's a problem for the defendants, the large corporations like Dow Chemical and DuPont and so forth. And I'll just show you, this is my last slide. This basically shows that there's very little correlation between lung disease, lung cancer and mesothelioma, if you're sort of part of the normal population. But if you work in certain trades involving things like blue asbestos, which is the chrysotile type asbestos, or the amosite type asbestos, then you have a problem. You have a much higher incidence of mesothelial cancer. Anyway, this has been a very interesting 30 years of working on this, because the attitudes have really begun to change now. For a while, everything was lumped together. So I thank you very much for your attention. Here are the same take-home messages that I gave you before. I'll skip those again now. I just want to go and thank George and the organizers for this, and thanks for your attention. Here's a picture of George, his wife Josette, Francois Farge, Kareem Benzerar sitting right there on my patio drinking. These were Mai Tais in preparation for our barbecue. Thank you very much.